Today I'm going to show you how you can open a NetCDF file in R, understand the contents, and extract the data and the metadata. This is going to be the first in a series of videos I'm going to make to show you how to work with NetCDF files in R, so if that sounds like something you might be interested in, hit the subscribe button. I'll keep the description of the video up to date with the current contents of the series, with links to all the videos. I'm also making a Jupyter book that you can use to follow along. That's also linked in the description, and it includes all the code included in the videos and written explanations too. There'll be one video per chapter. The main package that we're going to work with throughout this course is R NetCDF. There are other packages available, but I like R NetCDF because the syntax is very repetitive, and this makes it very easy to learn, as you'll soon find out. So we need some data. The data we're going to use today is the NOAA Global Surface Temperature Anomaly data. If you use these data in one of your own publications, please cite them, as is indicated here. I'm also going to include this citation in the description of the video. And also in the description you'll find a link to this page. To access the data, we're going to go to Access. We're going to access them via threads, the data in the NetCDF file here. And we're going to choose to access them via OpenDAP. Now, OpenDAP provides a way of accessing data across the internet without you actually having to download the file to your own computer first. So you have this data URL here that you can go and copy. And you can use this in your code when you're reading in the data, just like you might use some file path to some file on your computer. OpenDAP also provides a preview of the contents of the data, the global attributes that describe the file as a whole, which variables are included, and the variable attributes, which are the metadata that describe each variable. But I'm going to show you how you can access all of this in R. So if we go to RStudio, install the R NetCDF package if you haven't got it installed already, and import that library. And I'm going to do URL is equal to this data URL that I've just taken from the OpenDAP page. And on the line below, I'm going to create this object data. I'm going to make that equal to open.nc and this URL. So if I run all of that, and we've loaded the data into R. Now let's try and understand what the file contains. R NetCDF allows us to inquire about the file, so we can do file.inc for inquire.nc, and then our object that we've loaded here, this data. And if I run that, in the console, we can see some information about the file. We can see that there's 4 dimensions in this file, 5 variables, 66 global attributes, no unlimited dimensions. It's a classic NetCDF file format, and we can see the version of the library here. So I'm going to reduce this again. This is a dictionary, so if we want to access a single value from this, we could do, for example, in square brackets format, and we run that line again, and we just access the format. But often we're going to need a little bit more information than this, so what we can do instead is do print.nc and our object again, data. And if we run this time we get to see much more. If I scroll right up to the top, and now it's time to provide you with an overview of what the file contains. So NetCDF files have a standardized structure. So every file that you open should include dimensions, variables, some variable attributes, and below this, some global attributes. So if we look at the dimensions first, the dimensions tell us about the shape and size of our variables. So we can see that there are 36 points of latitude, 72 points of longitude. Note that this doesn't tell you anything about what the values for these dimensions are, just how many values you have. The values are within the variables, so we have this time variable here, and in brackets we can see it has a single dimension, which is time. And it's quite common for a coordinate variable like time, latitude, longitude to have the same name as its associated dimension. We can see that these values are floats, which means they're numbers with decimal places, and we have some different attributes that tell us about that variable. So the coordinate variables are at the top, and below that you have this data variable, this anom. And this has 4 dimensions: longitude, latitude, elevation, and time. And finally below that we have the global attributes, which are all the metadata that describe the data set as a whole. Now I'm going to show you how you can access some of the metadata first. So if I reduce the size of this, and I'm going to remove these lines for now. If we want to access an attribute, we can use at.get.nc. And you can see from this little yellow pop-up box here, the first argument we need to input is the NC file, which is data. Then we enter the name of the variable. So for example, anom. And then the name of an attribute. So for example, standard name. And if I run that, you get the standard name here. If you want to access one of the global attributes, in our NetCDF you can use the special variable name, which you call nc_global. And let's say we want to access a creator name to find out who created the file. We can do that. If we want more information than just the value, we can actually inquire about this as well. So at.inc.nc. See how the syntax is similar? And run this, and you have, instead of a value, the identifier for that attribute. So each attribute has its own number, the name of the attribute, the format of the values inside, and how many characters it has. And we can also call this just using the ID. So instead of using the name of the variable, we can do 16, and we access the same information. You might wonder why you might ever want to do that, but if, for example, you want to build some program that scans through all the different attributes, and you don't know what the attributes are called, then using the IDs instead of the attribute names could be useful. Now, perhaps the most important attribute within a NetCDF file is the conventions attribute. So I'm going to get that instead of inquire. Now, did you know that a NetCDF file is not necessarily compliant with the FAIR principles unless it adheres to certain conventions? So we often talk about NetCDF CF or CF NetCDF, which are NetCDF files that are compliant with the CF conventions. This stands for climate and forecast. And this is the version of the CF conventions that it's compliant with. And we also see the ACDD conventions, which is the attribute conventions for data discovery. So I'll explain a little bit about them now. So this is a CF conventions document. It's quite an extensive document, so you don't need to read all of this document, but this should be your go-to place if you want to know how to structure a NetCDF file if you're making your own, or if you want to understand the content of a NetCDF file that you have, and why that's structured as it is. So if I scroll through this, we can see, for example, if we have a latitude coordinate, there are some recommendations for how that data should be encoded, what the unit should be, and importantly, what the standard name should be. So this is a CF standard name table. So basically this is a list of terms that you can assign as the standard name to different data variables or different coordinate variables. So whilst the name for the variable, anom in this case, is not standardized, there's a standard name here, the surface temperature anomaly, which should be standardized. So anyone who's creating a NetCDF file with this type of data should include the same standard name. So we can find this here, surface temperature anomaly. And if we click on it, we open up a description. And you would hope that the data creator has read this description and has made sure that this is representative of their data. And you as a data user can also read this description. So the data user and the data creator have the same understanding of what the data are. And importantly, this also makes the data machine readable, because one can build services which can understand not just a single file, but all files that include this standard name. There are other things to look at in this document here. So for example, if we go to Appendix A, we can see a list of attributes that could be included. So you see the attribute names here, the descriptions, and whether those attributes can be used in C, coordinate variables, D, data variables, G would be global attributes, and so on. So this provides a list of attributes that the data creator should be including, but also it can help you as a data user to understand what the attributes mean. Now, the CF conventions are a little bit light on discovery metadata. Discovery metadata are the metadata that can be used to help someone find or discover a file. So, for example, when and where the data were collected, by whom, some keywords. And because this information is encapsulated by the CF conventions, we often see the ACDD conventions used, which is the attribute convention for data discovery. And this is basically just a list of terms which are either highly recommended, or if we scroll down, suggested, to be included within a NetCDF file. So in this case, we're just talking about the global attributes, but if you scroll further down, you also see some highly recommended variable attributes that are often included in NetCDF files, and descriptions of how you should fill them out. So that's enough about the conventions for now, but we will refer to them later and throughout this course. I'll quickly move on to dimensions, and just show you a single command that you can use if you want to inquire about that dimension. You can use dim.inc.nc, the name of your object, data, and the name of the dimension, for example, lat for latitude, and run this, and you see some information about that dimension. And now finally we can get to the most important part, actually getting at the data. So if we have at.get.nc for getting the attributes, we have var.get.nc for getting the variables. And then we have data for our object, and the name of our variable is latitude. If we run this, we can see we can access the data into a one-dimensional array. And of course, we can save those values if we want, like something like this. Then you can also do this by calling the ID of the variable instead. And alternatively, you can inquire about the variable. But I'm not going to do that for now. Now, sometimes we're not going to want to extract the entire variable. What happens if we want to extract a subset of the values? So we can do latitude subset and make that equal to var.get.nc, data, lat, and let's say we want to start with the fifth value from that variable. We can do start equals C5. And if we want to extract 3 values starting from that fifth value, we can do count equals C3. And if I run each of these lines and just expand this a bit, we can see that we've extracted the fifth value and 3 values in total. Now let's move on to our data variable, our anom. So let's call this anomalies. And again, var.get.nc, data, and this time anom for the name of our variable. And this contains a lot of data. So this time it might be important to extract just the subset that we need. So if I do in my console down here, print.nc and data, and if I expand this and scroll up, we'll remember that the anomaly values have 4 dimensions: longitude, latitude, Z, and time, and that order is going to be important. So what I'm going to show you how to do is access just a single time slice of this variable. So we want data for every longitude, every latitude, the single Z value that we have, and just a single time slice. If we minimize this, and then I can do start equals C. We want every longitude, every latitude, So we use NA. We only have a single value for Z, so we can just use 1. And let's first just extract an arbitrary time slice. So for example, 700. And then the count is going to be NA, because we need every value, 1, and 1, because we want just a single time slice. And I'm going to print this below as well. We can see our values, and if we look in the environment pane in the top right, we can see that it's a 2-dimensional array, 72 by 36. Now, in most cases, we're not going to want to select just an arbitrary time slice, but we're going to want to extract the data for a time slice of our choice. So let's revisit the time variable now. And if I do at.get.nc, data, time, and I want to look at the units for this, you can see that the units are days since the beginning of 1800. Now, this might seem a bit strange to you. Why aren't the times just timestamps for each value? Well, there are specific recommendations on how time should be stored in CF NetCDF files. I'll try to explain briefly, but there's also a nice explanation that I'm going to just link in the description to this video. So the time variable has to have units that are some count from a user-defined origin. So for example, hours since some time or days since some time. And this could be years, days, seconds, whatever. And whilst this approach might seem strange at a glance, it allows the times to be stored in a conventional numerical format, such as integers or floats, and to our desired precision. So this is much more efficient than using a long timestamp for each coordinate, for example. So some softwares know how to interpret this, and will convert the data automatically into timestamps when you open the data file. So for example, Xarray in Python does this. So does Panoply. Unfortunately, at the time of recording, our NetCDF does not. So if you want to extract data for a single date, I'm going to have to show you first how you can convert the date to these units, and then extract the data for that date. So let's do that. I'm going to scroll down a little here. Let's say we have a desired date variable. We can do as.date. And the date I'm going to go for is 2020-0101. Now, I know that this is a date within this file, but if you're in doubt, it should tell you on the landing page for the dataset. We see that these values are at monthly time intervals. So if I want to get the number of days since 1800, I can do that. I can use diff time to calculate the difference in time between two dates, and do that between desired dates and as.date 1800-0101. And I want the units to be days. We also need to make sure we're getting numerical values, so I need to do as.numeric. And if I run these two lines, we have a value that we can see on the environment here of 80,353. Now we're going to extract all of our time variables. So time is equal to var.get.nc data time. And we need to find the index within this array where the value is equal to this value here. So we can do time index, and that's equal to which time double equals days since 1800. I run these two lines. That value has been found. We can see the time index here. So now we just need to edit this line, and instead of using 700, we can put our time index here. If I run this, we've extracted our values. And there they are. So that's everything for this video. Now you know how to get data out of a NetCDF file. The next thing you might want to do is learn how to plot the data. So that's going to be the next video. I'll put a link to it here somewhere when it's ready. And if I haven't finished that video whilst you're watching this one, make sure you subscribe so you don't miss the video when it's ready. If you enjoyed this, give me a like and drop a comment below. And thanks very much for watching. I'll see you next time.